this video I'm going to go over Laplace transforms. So by definition, Laplace transform, so this is how you would transform it, a function of t, and it's given by this wiggly symbol or this rather weird looking L. So the Laplace transform takes a real variable t, or a function of t, and transforms to a function of a complex variable s. So according to this definition, we're going to do some examples. So it says find the Laplace transform of a function of t where it's just t. So if we show we're going to Laplace transform t, by definition we're going to have the integral with infinity and 0. We're going to have e to the power of negative st, and then we're going to have t. And of course that's with respect to t. So now what we're going to do is we're just going to integrate it. So this is integration by parts. So integrating, we would have e to the negative st, drop it down, negative s, and then multiplied. I have a separate video on integration by parts, which explains how I've done this. I've just done this mentally. Minus, and then we have another integral with infinity and 0. And of course we have e to the negative st minus s, and then deriving t is just 1. And then we have with respect to t there. So then, if we finish this integral, I usually put them in square brackets. We have negative, if we just put this negative up here, negative e to the negative st divided by s, and that's multiplied by t of course. And then we also have negative e to the negative st over, and of course that'll be s squared, because you drop another s down. It's negative because we have a negative here, so negative makes positive. Of course we close that bracket, have infinity and 0. So with integration, once we have the range, we need to input them in, but since you can't put infinity, we use limits. So if we add a limit, say that we use t, for example, capital T, as it approaches infinity. So that's how we would rewrite it. Capital T and 0. So now that we've done that, we can substitute in the integration bounds into t. So if we sub in, or assume a very large number, because it's t as t approaches infinity. So when we submit a very large number into e to the negative st, it'll become e to the negative of a very large number. And if you look at the graph of e to the negative of a very large number, it approaches 0. So because t approaches infinity, then this value would approach 0. And then we have minus, and the same goes again here. When we submit a very large number into this t, we get 0 as well. So now we would minus and do submitting, and then submit 0. So if we put 0 in here, you see how this would equal 0. So we'd have another 0, and then that'll be minus. So we put a very large number into this one. So, we put 0 into this one. So when we put 0 into this t, the whole upper area will become 0. E to the power of 0 is 1. So we will be left with minus 1 over s squared. Then if we get rid of all the zeros, we'll just be left with 1 over s squared. So that's the Laplace transform of t. In upcoming videos, we're going to be doing Laplace transforms with tables. So these would be calculated Laplace transforms using this definition. If we do another example, find the Laplace transform of this function, where we have e to the power of alpha multiplied by t. So if you write it out again, this time our function is e to the negative st, because that's according to our definition up here. And then we've also got this function e to the alpha t, and then of course that's with respect to time. Oh, sorry, t. So now we're gonna integrate it. But before we integrate it, we can combine these two variables because they have the same base. So we could actually put e, and then we can pull out t, factorize, and then we're left with alpha minus s. And of course that's still with respect to t. So once we've done that, it makes it a tiny bit easier to integrate. So we don't have to do integration by parts. This can just be integrated. So we're left, if we pull this down, we would have e to the t alpha minus s, and that's all divided by alpha minus s. And of course we still have infinity and 0. So what we're going to do here, as we did with the previous example, is add a limit. So lim as t approaches infinity, vt alpha minus s, alpha minus s, t 0. So once we've done that, what we're going to do here, before we input in our integration bounds, we're going to assume that s is larger than alpha. So this means that e to the negative of t, so we're going to assume that it limits towards 0. If we didn't make this assumption, then there would be no solution, as it would just keep going to infinity. So we need to assume this in order to find the Laplace transform. So once we've done that, as we've already established that s is larger than alpha, when we input infinity, this term goes to 0, so we have 0, and then we input 0, when we put 0 into t, it becomes e to the power of 0, which is just 1, it's 1 over alpha minus s, which is equivalent to 1 over s minus alpha. And that's it. That's how you find the Laplace transforms.